So I think you all agree that the solar system is a pretty dynamic place.
Yep.
Things are on the move. Most of the orbital motions that we think of from day to day are pretty predictable, straightforward sort of motions. We know that the Earth just constantly goes around the sun, and every year we have our birthday, those birthday packs and candles chase us around the place. The moon goes around the Earth every month, that's all fine. We know that Mars no time soon is going to be a threat to us. But there are some events that catch us by surprise. You might be having your morning cornies, enjoying your peace and quiet, and suddenly a news item comes up, whoa, asteroid on its way, coming awfully close. So you can't help but think to yourself, what forces are in play out there that suddenly makes a nice, friendly asteroid minding its own business in a stable orbit in the asteroid belt say, yippee, let's head down to planet Earth. What's going on? And that's why tonight I want to have a chat with you and let's together explore the forces driving orbital motion in the solar system. So we get an idea of what is behind that rogue asteroid. I'm going to come straight out and tell you right up front, your take home messages, no. So, gravity's a big player. No surprise. The other one is solar radiation. Don't think too much about. That has an effect. Gravity is the prime driver. That's the key to it all. Its influences can be relatively simple, which we'll go over and discuss some examples of. The influences, however, can be a little bit less than simple, a bit complex. The Yarkovsky effect is the main effect from solar radiation. Who here in the room has heard of gravity? Here we go. Yeah, we've all heard of gravity. Genuinely though, how many people in the room have heard of the Yarkovsky effect? Yeah, few, but certainly much less than people have heard of gravity. Not talked about around a lot. That can initiate trouble. Put that together with gravity and we could have a problem on our hands. So we'll talk about that. So first of all, let's talk about gravity as the prime driver. As I mentioned, you can have some influences that are relatively simple, influences that are a bit more complex. So we'll grab a couple of examples out of each of those just sort of to illustrate the point. Simple influences. Let's talk about Newton's law of gravitational attraction. That's essential to a lot of behind the planetary motions we see. And it naturally leads on to Kepler's law of planetary motion, which hopefully a lot of you are aware of. May not be what it's all about, but aware of them, which we'll go over. That's a good opportunity to review those. So, Newton's law of gravitational attraction. And presumably, you've all seen this sort of type of formula. It's in your little handout sheet there. You get two masses here, two bodies, and there's a gravitational attraction, to a force attracting these two bodies together. And this is the formula, F1 equals F2 equals V M1 M2 R squared. Now, what that means, in most equations, it's not important to know how to derive the equation. What's important about any equation is know the implications of the equation. So first implication here, F1 equals F2. And you naturally think if you get two bodies, that the big one must be pulling the other one closer. But it's actually not so. What's actually happening is both of those two bodies are experiencing equal force. And just to help me, I've got some sort of props here. This is going to be the best thing I could find for sun. It's actually a Mars globe. What sort of nerd is a Mars globe at home? The cat's got to be So pretend that's the sun. And here's, for example, or a Mars, an asteroid. I think Kuiper is my great asteroid. I just looked at it and thought, that is an asteroid. Look at the shape. Look at the little belt on it. Perfect. So you've got the huge big planet here and smaller asteroid out here. You'd think that, oh, the force, there must be greater coming from here. But in actual fact, that formula implies that this asteroid, aka Kuiper, is actually experiencing the same attractive force as the big planet, or might be the sun. The forces are equal, it's just attraction. No one of them is pulling, this one's not pulling this way, that one pulling that way. They're both coming together, they're both experiencing the same force. G is a universal gravitational constant. Of course, there's three big universal constants. C, the speed of light, the little h for Planck's constant for energy, and G, the gravitational constant. M1 times M2, that means to calculate this force, it's dependent on the mass of these two forces. As the mass of these two objects increase, so does the attraction between them. It also implies that should you double the mass of these two, the force between them doubles. Of course, if you double that and double that, the force will be 4 times. But if you, essentially, it goes up in proportion. The other fact is that it's divided by the square root of the distance between them. And that's really significant.
Square.
Sorry, the square root, the square. Divided by the square, pardon me. Carried away there. So that immediately has implications. You start spreading these apart and the gravitational force drops away quite significantly. So if you double the distance between these two objects, you're going to actually drop the force by a factor of 4. You say separate them, say 5 times the distance, the gravitational attraction between the two is going to drop off by a factor of 25. So those are the main implications there. They both feel an equal amount of force. It's proportional to the total multiplication of the masses, and it's divided by the square of the distance between them. So, Newton's law in a nutshell, what does that imply? Well, it's certainly that the force between the two, you've got a big sun, and you'll learn from last time we spoke about the sun makes up 99.9% of the mass of the solar system. So the sun's influence on the planetary motion is by far the largest, because you're even multiplying one of these, or a factor, the sun and one of these other factors together. And the forces declines very quickly as you go further out in the orbit. So for example, the gravitational attraction between Neptune and the sun is going to be hugely less than that, say, of Earth. So that's Newton's law in a nutshell. So that moves on to Kepler's law of planetary motion. And I might just go back a slide here, just this here, because in school you always learn Newton's law of gravitational attraction, and you use that to derive Kepler's laws of planetary motion. But in actual fact, historically, the dead opposite happened. It all started in the 1500s, and a guy by the name of Tycho Brahe carefully plotted out, observed, and wrote down all the positions of as many planets he could find. Then in the 1600s, a guy by the name of Johann Kepler went over all those figures, mapped them out, worked out, calculated them, and he came up with these laws of planetary motion, which we're going to look at shortly. And from there, in the 1800s, Newton got those, had a look at them, and from there deduced the universal law of gravitational attraction. So it actually happened in the opposite to what we intuitively think it would have happened. So Kepler, he got all these observations, and without any universal laws, he just worked out there's got to be some patterns here. And indeed, he found 3 patterns. And he created his 3 laws. The first law says all planets move in elliptical orbits with the sun at one focus. Well, that seems obvious, doesn't it? Well, they didn't know. You just assume that everything goes around in circles. He was one of the first guys to say, look, planets don't go around the sun in a circle. They go around in an ellipse. An ellipse essentially is an elongated circle that has 2 foci, and the foci are points at which the curves of the ellipse are focused on. And usually, when something is going around another object, such as here with the planet going around the sun, one of the focus, the sun sits it there, and the planet goes around in an elliptical fashion. The Earth's orbit around the Earth is not far off a circle, but it's not a circle. Then you get planets like Mars, which are very much more elongated. Here's law number 2. So a line that connects a planet to the sun sweeps out an equal area and equal times. That's what he's referring to there. For example, take any month. Say this is, well, when you're going closer to the sun, who can tell me what month this would be? What season for us here on the southern hemisphere? Summer, yeah. So say that's mid-December through to mid-January that made it a month. That's going to fly by a lot quicker than, say, when we're having our winter over here. And the reason being, of course, is because you're closer to where the gravity is. So we're about short change down, aren't we? Get a shorter summer. So,
We're closer.
but we're
Slightly closer to the fire.
yeah, exactly. Yeah. So, yeah, so that's what he's saying here, is that if you happen to be closer to it, you travel a lot faster than if you're further away in terms of within the orbit. So essentially the orbit will go zoom around here, slow down, go slow, pick up again, zoom around here, and so on like that. So that was the second orbit. Pretty amazing stuff, wasn't it? A guy working this out just from a set of figures that someone had written down from their observations in the night sky, where planets were positioned. This third one was equally amazing, if not more. He worked out the square of the orbital period is proportional to the cube of the semi-axis. Let's go back to the second orb. Sorry, what's it? So let's go back to what a semi-axis is. So essentially, what you do is a circle, of course, is just a radius. It's easy, same point the whole way around. With a ellipse, you get the longitudinal axis called the major axis along here, then you split it in half, and that's called a semi-major axis. And that's what they tend to, it's one of the sort of major properties of an elliptical orbit. So what he did, he worked out all the semi-axis, the semi-major axes of the planets that he was observing. He put those here along the x-axis. Along the y-axis, he then got the orbital periods, cubed those. Actually, I've got that wrong way, haven't I? I've got here. Cubed the semi-axis is cube 3. No, that's right. Plotted the square of the orbital period, in other words, the time that it takes to go around the sun, against that of the cube of the semi-major axis, and whammo, a nice straight line. And obviously that's how that comes out from that equation, that the square of the period, or the time it takes to orbit the sun, is equal to the cube of the semi-major axis. And the implication of that is that if a planet's much further out, like Neptune to Earth, that we spoke about before, it's going to be travelling a lot slower and take a lot longer. A year on Neptune will be many, many years. I'm guessing it's about 150 or something like that Earth years. So, Kepler's law in a nutshell. Law number 1, planets orbit the sun in an ellipse, not a circle. Planets travel faster when they're closest to the sun. And the larger the orbit, such as Neptune and so on, the longer they take to go around the sun. I think Pluto takes about 240 years or something like that, doesn't it? Not that it's a planet anymore. So let's move on. So that was just really covering the sort of relatively simple effects and influences that gravity has on the orbital motions in the solar system. I'd like to move on now and discuss some of the a little bit more complex influences that it has. That is very relevant that we see from Earth.
What did that word to me?
I'm going to go over those. Yeah. Perturbations, we're going to go over all of these. Good question. No, perturbations means disturbances, probably in one word. Means disturbances, and resonance we'll talk about too. Let's line up. Good questions. We're going to talk about those. So perturbations or disturbances. We're going to talk about orbital precessions, which we're going to talk about, and then the concept of centaurs, and then as examples of resonances, we're going to talk about the moons of Jupiter and Saturn and the asteroid and Kuiper belts. The reason I put that slide up as a road map so you know how we're progressing. Sorry? Resonance. We're going to talk about that. Yeah, I just put this slide up as a road map for you so you know how we're talking. We're going to talk exactly what resonance means. Yeah. Okay. So perturbations or disturbances, and there's sort of two interesting things that opens it up from that is orbital precession and centaurs. So let's talk about what orbital precessions are. When you think of a planet, say Earth going around the sun, you always think that Earth just going around the sun and it just does this and this and this and this for millions of years. That's not what happens. Because of the influence, sure, the sun's the biggest influence, but you can't forget about those other planets, particularly the big ones sitting further out, Jupiter and Saturn. They do have an influence on the way that the Earth orbits the sun. And for that reason, the orientation of the orbit is constantly changing. So it might be going something like that, it's getting a little bit more tilted, and it might swing back again, and so on. So the orientation of the orbit is changing. So you can see it's sort of tilting that way, and so on. And that's all due to the gravitational influences of the other planets. Similarly, I can show you on this one, so that's an orbital precession. That's just a technical name for it. If the plane of an orbit is like that, and it's slowly swinging and altering its orientation, that's called an orbital precession. Equally, if you get a planet, this is my other planet Earth, this axial tilt, 23.5 degrees, it doesn't just sit there and spin like that forever. Over the years, that axial tilt is, well, the tilt does change, but also its orientation of the axial tilt does change too. And that's all because gravitational influences of the other planets. Our sort of axial rotation precession is actually a little bit less than a lot of the other planets, because we've got a nice big fat moon next to us helping to stabilise our axial tilt and precessions. But the Earth does a bit of a rotational or spin precession. So that's what the word precession means. Precession is all caused by the influence of the other planets. You can't forget about them. They're out there, they remind you. That whole process is part of what's called a Milinski cycle. Happens over about 26,000 years. A guy, I think it was Milinski who did it, calculated all this with pen and paper while in a prison in some, I think it was a prisoner of war or something like that, and he was just had a clever mind, was bored crazy, pen and paper, and just calculated it all out.
This the lantern that Chris you talking about?
Yes. So that's orbital precessions. Another one is to do with perturbations is centaurs. So let's just talk about, first of all, comets. So here's the Kuiper belt, it's a collection of small bodies, millions of small bodies outside the orbit of Neptune, and they are thought to be the source of comets, short period comets that start heading into the inner solar system. Now you might think, once again, like that asteroid question we posed at the start, what suddenly decides a little object here, think, oh, let's go and visit Earth, let's head into the inner solar system, up it goes. It's usually a slow process over millions of years that happens. They don't automatically turn into comets. It's almost, there's a state called a halfway sort of, or a hybrid state. Of course, you know what a centaur is. It's a mythical creature, half horse and half human. So it's almost like a halfway or hybrid state between being a Kuiper object and a comet. And here you've got Uranus and Neptune are the big players here. Their gravitational pull is constantly pulling, causing little gravitational perturbations or disturbances and nudging these guys out. They don't necessarily head straight into the inner solar system. They become centaurs. And I've put this up here. It looks a bit messy, this diagram, but that explains what a centaur is. It's an object that doesn't head straight into the inner solar system. These are some of the centaurs that have already been discovered and named. And you can see they head from the outer solar system, they head in, but they don't head inside the orbit of Jupiter. They sort of roam, but sort of comets are very nomadic. And the nomadic, like comets, but they stay outside the orbit of Jupiter. And they're called centaurs, like hybrids. And that's what that slide is all meant to represent. There's a handful of them, it's just a handful of them. They're getting names for them, they're getting identified. So they're sort of halfway hybrids between becoming a full comet. And you might think, big deal. Well, one of those one day might seal our fate. You never know. They sort of, all it takes is another perturbation and they become a proper comet. So, moving along, so we've talked about perturbations or disturbances. We'll now explain what resonances are. And two good examples of resonances influence sort of gravity in the solar system are the moons of Jupiter and Saturn and the asteroid and Kuiper belts. So we'll move along. Now, what a resonance means is that in this context is because if there's a mutual, so here's your moon, here's Jupiter, and you've got three of its main four moons all going around Jupiter. They all are mainly influenced here by, of course, the attraction to Jupiter. But these guys out here also are influencing one another, and because of a gravitational attraction towards one another, the orbital periods all line up from time to time, and their ratios are always of whole numbers. Now, Io, that's the inner one. For every one orbit that Io does, Europa lines up every second orbit. You can just watch it, it's going a bit quicker than I had it going this afternoon. But you can see every second orbit, let's look it up here, there it is, lined up. Lined up. Lined up. Ganymede is a 4-to-1, so for every once orbit of Io, Europa does it twice, Ganymede for every 4 loops of Io, Ganymede does 1. And you'll see them in a minute, you'll see them all line up. Here it comes, there it is, all lined up there, it's just happening a bit quickly. So Io, for every 2 laps of Europa, Io does 1, and for every 1 lap of Ganymede, Io does 4. So now, you might say, big deal, that looks pretty, but that's the key driver behind all the volcanic activity on these icy moons out here. Because you've probably seen pictures of Io volcanoes, you've heard of Europa and Enceladus around Saturn, how there's subsurface global oceans of liquid water, there's geysers shooting water high in the sky into the air and so on. You think, where's the energy driving all that so far out in the solar system, so far out from the sun and so cold? It's these forces that are constantly pulling and tugging on the moons that create all this flexing inside them, which creates energy. So that is very relevant. Let's move on. Another interesting example of resonances is in the asteroid and the Kuiper belt. And this is, once again, it's all the game of whole numbers. That most throughout the asteroid belt, all that are in nice stable orbits, but there are little gaps where there are no asteroids, or very, very few of them. They're called Kuiper gaps. And they're in little areas of resonance where if you happen to be an asteroid sitting here, you're doing 3 orbits for every Jupiter's 1. Jupiter is on the outside of the asteroid belt. This is between Mars and Jupiter. So if you're sitting, happen to be right there, you'd be doing 3 orbits around the Earth for every 1 orbit around that Jupiter does around, start again. You'd be doing 3 orbits around the Sun for every 1 orbit of Jupiter going around the Sun. If you happen to be here, it's a region called 5-to-2 resonance, you'd be doing 5 orbits around the Sun for every Jupiter's 2 orbits around the Sun, and so on. Here is the 7 orbits around the Sun in this position for every time Jupiter does 3 orbits around the Sun, and so on. These are 2-to-1. Those are regions of orbital resonance with Jupiter, and those are very unstable. To get those with a big planet on the outside of you and the Sun, you get biffed out. You get turfed out. It's a very unstable orbit. That's why you don't see many asteroids sitting there. So those are called Kuiper gaps, and they're regions of resonance between asteroids and Jupiter. Unstable resonances. And it's all about whole numbers. That looks like looking down on the asteroid belt. You can see nice strips where there's concentrations of asteroids, but look at these little gaps. And those are Kuiper gaps, where there are orbital resonances, where they are unstable because they have a constant, regular tug, and that's the key to it. It's a regular tug from Jupiter, and they get biffed out. Similar concept, but totally contrary to that. The Kuiper belt, and that was that collection of millions of small objects that lie outside huge Neptune. Remember, the asteroids were inside the orbit between the Sun and Jupiter. If they had a resonance, they got constant tugs from Jupiter, they get biffed out. The dead opposite happens here if you happen to be on the other side of the large planet. So you've got Neptune over here, you've got all these millions of small objects making up the Kuiper belt here. And where you've got regions of resonances, they are stable areas. They prefer to stay there. And that's where you get concentrations. And this is a map here of locations of various Kuiper belt objects. The 2 big resonances is 1-to-2. In other words, for every 1 orbit of the Kuiper belt, you get 2 of Neptune. And how do you work? Well, see those ratios out, and that's why I've got to stop and correct myself. Remember what we talked about with Kepler's law? Something that's closer in travels a lot faster, something further out travels a lot slower. So you think, which is going which? Obviously Neptune's the inner, so it's going around quicker. So for every 2 orbits of Neptune going around the Sun, the Kuiper belt in a particular region in a 1-to-2 resonant location will only be going once. Similarly, 2 and 3, so there are places actually here, these bits here, there are 2 to 3 resonance with Neptune. In other words, if you're sitting here, you would go around the sun twice, and at the same time Neptune would be going around 3 times. And it's that regular sort of attraction to Neptune that keeps these areas stable. And I've put in there, you might say, well, where does Pluto sit in here? Pluto's in one of these groups of 2 to 3, and that's at just short of 40 astronomical units. An astronomical unit being the distance from the Earth to the Sun, which is about 150 million kilometres, so you're talking about 40 times the distance from the Earth to the Sun out here. And roughly just under 40, that's where Pluto and all the Plutoids sit. So that's a similar concept. If you get a whole number ratio between your orbital period and a big giant's orbital period close to you, that giant has an influence on you. If you're closer to the Sun, and that time of that constant tugging and pulling on a regular basis, you get biffed out of that orbit. If you're on the other side of that large object of the Kuiper belts, you like it there. It seems to stabilise you there. And that's why these orbits, such as Pluto, that does throughout its orbit cut in front of the orbit of Neptune. People say, will it ever collide with Neptune? No, it's in a nice stable orbit. It'll always keep its distance there. So, gravity in a nutshell. It is the prime driving force behind pretty much most of motion we see. It has influences either in a simple manner or some more complex manners, such as we talked about with disturbances or known as perturbations, or those areas of resonance where you're getting a regular tug from another object and influence whether it's a stable or unstable position you're in. We talked about with the simple Newton's law of Kepler's laws, in other words, how the planets go around, why they go around in that manner, because of the laws of gravity. Complex influences, how the orbits precess, so the orientation of the orbit changes, is going around the Sun because of the gravitational attraction of the planet. The centaurs, that's objects and it's happy in the Kuiper belt. Eventually they just get frequently tugged, probably venturing out of those areas of orbital resonance. You venture out of there, they get thrown into wild orbits, just unfortunately are outside the orbit of Jupiter, but further tugs can bring them into us. The resonances, as we've spoken about, that's where you get a whole number, integral number, a ratio of your orbits around the Sun with another objects around the Sun. A regular pulling on it throws your orbit out or holds it stable. And that's it. So, this is just a map, doesn't mean take home message, just reviewing it. Gravity, prime force, simple and complex influences. Let's move on to solar radiation. There's quite a few things that the Sun has effect on. Radiation pressure, that refers to photons when they come out of the Sun, travel throughout the solar system. They actually do have some momentum. You might say, but aren't they massless? They are massless. Photons do have momentum. They will affect, but it's only on small, tiny little granules that they have that effect on. So it doesn't really affect the bigger objects like Kumas. Pointing Robertson drag is another thing where we get solar particles heading out to the solar system. They tend to interact with small particles. But the big one we want to talk about tonight is the Yarkovsky effect. That's the one of concern to us, because that solar radiation effect affects the objects as big as the asteroids. So let's talk about that. So what is the Yarkovsky effect and why should we care? Well, there's a few concepts to take in here. First of all, objects absorb the Sun during hot days, in the middle of the day, and that's hence by this nice black family dog here soaking up the Sun. He's warming up, he's enjoying out the sun there because he's absorbing heat. He's warming up while he's in the sun. This slide represents the concept that at night time, when the sun goes down, those objects that have warmed up during the daytime are now radiating heat. And here's your footpath in the road. You see all the cats. If you watch your family cat, they'll go out and lay up in the road with the footpath for the night, because that's where it's warm. It's radiating heat at night time when the sun's gone. The other principle related to the Yarkovsky effect is Newton's first law of motion and forces, that for every action there's an equal and opposite reaction, and that's how rockets essentially work. You start putting fuel out this way, and your rocket's going to head that way. Well, you've got radiation coming out this way. You don't feel it because it's minimal to the Earth, of course, but the Earth is being pushed back down. For every force, like radiation going up that way, you've got a force, an equal and opposite force going backwards. And those three concepts are key to the Yarkovsky effect. And here it is here. So I'm going to explain a little bit, and then I'll brought my little props here. Some concepts. Asteroid, there's an asteroid there, or could be a Kuiper. They go around the sun just like planets. We call this the sun. Asteroids rotate. They don't just quietly zoom around like that, but like any planetary body, in fact, almost everything in the universe has a degree of rotation to it. So it's that asteroid is rotating as it's going around the sun like that. So, just like it experiences a night and day. Just what things do when they rotate around the sun. The surface facing me is now in daylight. That same surface is turning away from the sun. It's turning into night. The other side's warming up in daylight, just like days and nights on the Earth. And also, that surface is no different to our road surface and our footpath surfaces. That surface on this side, with my thumb facing the sun, it's warming up. And what does it do when it turns to night? It starts radiating heat, usually about in sort of the early evening. And you know yourself, when is the road and footpath the warmest? In the early evening, and come about 2 or 3 o'clock, and it's well and truly cooled off. It's not so warm anymore. It's the same principle with your asteroid and Kuipers. And once again, this is probably trying to explain a bit further, but here's a little bit of orbital mechanics as well. So you've got your asteroid going around the sun like that, warming up, turning around like that. Now, let's make it, I'm going to introduce the concept of prograde and retrograde. If something is going around the sun, say anti-clockwise, and it's rotating anti-clockwise, that's called prograde rotation. If it's going around the sun like that, but it's rotating the opposite way, that's called retrograde rotation. Planets are all usually prograde because they're big and they've been made. It's a long story with the planetary nebula and so on. But asteroids, they're a bit small in influence, so some of them do rotate the other way. Where I'm leading to is if you've got a prograde, let's look at both examples, but let's have a prograde asteroid travelling around the sun, going around this way, warming up on the side, it's rotating prograde, it rotates around this way, it's early afternoon, so late afternoon, early evening, it's starting to radiate heat this way. What does it do? Newton's law, for every force there's an equal and opposite force. It pushes that out, that way. A bit of orbital mechanics, when you are going around something and you get pushed out further out, you're actually slowing down a little bit, but you're getting further out orbit. So the other principle is that if you happen to be going prograde as an asteroid or a Kuiper around the sun, you're going like this around, you're heating up here, daylight heating up, you're turning this way, you hit late afternoon, early evening, that's turning dark, you're starting to radiate heat that way, so that's pushing you this way, and that's driving you back, slowing you down, and bringing you into a close orbit. So what I'm saying in a nutshell, with the Yarkovsky effect, an asteroid going around the sun, if it's rotating prograde, it's getting nudged out of its nice stable orbit, and if it's rotating retrograde, it's going to get nudged closer towards the sun. The one going closer to the sun can just drift quite happily, just carry on drifting right forward and come and say hello to us, which is a concern. But even if it doesn't get that far, or even you might think, oh, the one that gets driven out away from us, that's great, that's one less to hit us. No. What have we just talked about? Kirkwood gaps in the asteroid belt, those areas of orbital resonance. All it takes is an asteroid, say the middle half or so of that asteroid belt, it's going prograde, it's rotating around, slowly the sun starts radiating its heat back that way, pushes it out, and it takes billions of years with that little asteroid over millions of years will get pushed out. Sooner or later, it's going to hit a Kirkwood gap. What happens? Jupiter says, nah, kiddo, you're out of there. Just it out our way. And gravity is a big force. That's how these things get closer to us. tiny asteroid that's going around. It warms up, it radiates heat which creates a force in the direction of its motion, so it's going forward and rotating in the prograde. The force pushes it out. The force also can slow it down, that's if it's retrograde, which means it drifts inward. So depending on which way the asteroid is rotating itself, it'll either allow it to drift inwards or it'll push it out. But the bottom point is, the main point here is that solar radiation just over time will nudge that asteroid out a bit further or bring it back in. It'll do either or, depending on which way it's rotating. And then it will hit those Kuiper gaps. That's there, that's illustrating here. Prograde rotation, it's rotating that way, so it's going to radiate heat that way, which drives it outwards. And this one here, it's going the opposite way, rotating the opposite way, the heat gets radiated back towards the way it's going, and it slows it down and pushes it in. But I think the Kuma and the Mars globe are far better example.
Just point out, because this isn't just theoretical
No.
concept, it's actually been measured by radar of asteroids that have get close enough to the Earth that can bounce radar signals off them. They've measured these asteroids over multiple orbits, and they can actually see this effect actually happening.
What sort of very nudge do they get?
Very tiny.
It's millions of years for this to take effect, but it's real. It's real. See, there's a mission up here now. I've got a quirky little video, but I just wanted the sound doesn't play, but a lovely little quirky video about the science mission to only explaining it all and stuff, but I've got to get that going in a couple of weeks because I've got some.
Does that mean that all asteroids that eventually do hit a Kuiper gap?
Well, not necessarily.
No, I wouldn't have thought so. It's just enough anyway to be a concern. This book says it's measurable. It's not. This is not theory. It's for real. So that's it. The inward outward drift hits a Kuiper gap, becomes what they call a near Earth orbit. That was my video. Should we just play this now? I've got a hunch it's not going to play. Even if I no, it's not going to play, is it? Well, anyway, you get the gist of it here. This is just actually just for fun. Okay, so it's a little science session. We're talking about the Yarkovsky effect. And here you go. Here's your friendly dinosaurs. They learned all about this long before we did. After silent movements. So here we go. So they're talking about the one that hit Russia. It was about 3 or 4 years ago in Russia. A large asteroid came in. That's what they're talking about here. So that's telling us we've got to understand asteroids and what happens to them. Which is what the mission. Yep, harmless meteorite can be of harm. Asteroid rather can be a meteorite can be of harm. There's your solar radiation hitting it. That's Yarkovsky, the Russian, the guy who first postulated this idea, which has since been proven. Getting absorbed, heating the asteroid up during the daylight. The asteroid that I don't know if it's going to rotate it here, you can see the asteroid's giving off here. Here they're giving the example of the road. It's a lovely example of roads and pavements, warm up during the daytime, late afternoon, early evening, they're hot as. That's where they do most of their re-radiating. Snakes enjoy it. Yeah, there's the asteroid rotating. Now radiates its heat. satellite mission that's up there at the moment, that's measuring these movements. There you go, there's a website, we're going to look it up, asteroidmission.org. Yeah, so that's a little quick little isn't it? Yeah. Okay, so near-Earth objects, we are rogue one might be of. There are over 10,000 known near-Earth objects already. And that just gives you a stack of them. Now, these ones here that I've named are just some of the main ones that are still going through the asteroid belt. Just some of the big ones that have been noted. You can see here, here's the Earth orbit here, there's Mars, and there's the asteroid belt here. So they're out there. 10,000 that have been known so far. Of course, they're going to discover more as they get better at seeing them. And yeah, we should care. If you're still not certain, go and ask the dinosaur. Oh, I forgot, they're no longer here, are they? I wonder why. So, take-home messages once again. Gravity and solar radiation are the two forces that really are moving the solar system about. Gravity is your prime force, works in nice simple ways, but also much more complex ways. In particular, we've learned about the Kuiper gaps for the resonance, is probably more relevant. Solar radiation, most of you learned a new word, Yarkovsky effect, from Ivan Yarkovsky from Russia. And yep, that can initiate trouble. So I hope you've enjoyed us exploring the forces driving the orbital motion. And when you go home tonight, I just want you to reflect on next time you hear in the paper or something like that, that an asteroid's heading this way, just have a quiet thought about what forces are in play to make an asteroid that's happy and comfortable in a nice stable orbit, an asteroid belt suddenly head our way. Just something where you know now, the Yarkovsky effect, into an area of orbital resonance with Jupiter. Jupiter shoves it our way. So it's a combination of Yarkovsky effect and gravity, which you get into trouble. But most of all, when you're on your way home, drive safe. Thank you. Any questions about that, or how to grow permanents or anything?
Chris, I'll just point out that Yarkovsky effect is also considered to be one of the ways that could be used to protect the Earth from asteroid collisions. If you have enough time, warning if you like, you could paint one side of the asteroid black. If you knew that asteroid was going to hit the Earth, you could deliberately modify the asteroid so that, given probably a few thousand years advance warning, that would be enough for it to miss the Earth. So.
Bruce Willis and his team are on standby now.
I read somewhere that they're predicting there's an asteroid that's going to hit the Earth, one that's, I think, 500 metres in diameter, in 2036. Will become very close. I reckon one of the American newspapers.
Fake news.
And that's what people say, why are we going to Mars? Why don't we look after Earth first? We don't want to be a species that's reliant on one planet. All it takes is one mishap and wipe us all out. It's an insurance policy against these sort of activities. Yeah, right.
Does it generate much gravity, those asteroids? You know, they said they rotate. Wouldn't generate much gravity, would it?
No, well, it's the rotation that doesn't create gravity as such. They've got very low gravity because of the low mass, and you've seen the spacecraft that land on them, they bounce, a comet or an asteroid, they bounce quite a bit. They rotate, I think you're talking about, you're counting in hours at which they rotate, like about 10 hours or something like that. They rotate relatively quickly. Yeah.
Yeah, I've got a Crookes radiometer at home. Does it use the same effect as the Yarkovsky effect?
You've got a what, sorry?
A Crookes radiometer.
Tell us about a Crookes radiometer.
Oh, it's a vacuum bulb. It's got a device that spins inside it. One side's painted black and one's white. The light shines on it and spins.
Yes.
It's the same thing.
Yeah, it's the same. Yeah, I know. You only it at school, science. Yeah, it is the same thing.
The sun and
Yeah, but it's rotating, spinning around. But, yeah.
So that's the same as the Yarkovsky.
That's different, that's actually affecting its rotation, and that's another effect again. It's the sort of that pointer drag effect involved with that, how it affects actually the spin. It's a little bit different. This is more of a motion as it's rotating. So that sunlight's not affecting its rotation, it's more effect of the sunlight and the rotation that's propelling it. A little bit different, but the same principle how the photons, that's actually more of an illustration of your photons having momentum too, and reflecting. But there's an element of that in this here.
Why does the Yarkovsky effect, it obviously has a bigger impact on small objects with no atmosphere than it does on major planets?
Yes, because of, you don't have an atmosphere, so you have a surface to heat it up and re-radiate it off a lot easier. The atmosphere, our atmosphere soaks up a lot of that radiation. And also you've got the atmosphere that blocks it as well. A lot of the radiation is blocked by our atmosphere. And we're a big object to turn and try and move as well. There's an optimal size for which all those effects work, and those other ones I showed, those other effects usually work in just grains or dust grains. The Yarkovsky effect works best on those sort of asteroids, filled up to about 50 metres or so. Yeah. And I think you'll find it would be big enough to move a planet or such, and you've got the atmosphere as well. It's more of a combination of a decent size, but not too big of a size with no atmosphere. Okay, we're all good. Yep. So drive home safely and look out for the Yarkovsky effect out there.
Just before you go, if you haven't already seen it, the Harry Williams Trophy entries will be printed. They're on display down in the Mandaree room. If you haven't seen that, be